Alright, let's get started. Hi everyone, I'm Nathan. This is Alex. We are here to present to you the software-defined distributed QoS system that we developed at Bloomberg. It's to ensure the performance of our Ceph clusters matches what our users need. So I'm going to go through some of the design decisions and I'm standing away from the mic. So I'm going to go through some of the design decisions and the influences that went into, I don't know why I'm so nervous, into the system. And Alex is going to go through the actual implementation. So let's get started. Okay, so firstly, I'm going to go over an agenda. I'll talk about who we are, a little bit about our Ceph clusters, set some expectations that our users have for the system, how we go about managing performance of the system with QoS, some of the alternative approaches that we looked at as part of this design, what our solution actually looks like, some plans for the future, and then finally at the end we will be taking questions. So, Bloomberg, if you have not heard of us, we are a financial technology firm. We were founded in 1981. Our flagship product is called the Bloomberg Terminal. Essentially, our clients use it every day for various data services, news, analytics, basically anything that pertains to financial analysis. Basically using it to influence what they want to do with their money. We have hundreds of thousands of subscribers all over the world. We process hundreds of billions of pieces of data every single day. We do it with a force of about 7,000 engineers. Within Bloomberg, we have the storage engineering group. We are responsible for designing, building, and maintaining all of the storage provided to the rest of Bloomberg engineering. So we have both appliance-based and software-defined storage solutions. We have the three major pillars, so you've got file, block, and object. We have data protection workflows, so automated backups, redundancies, that sort of stuff. We also have teams dedicated to various, workflows and automation, so letting users onboard themselves, manage their quota, all that sort of stuff, so that we don't have to do it. Within the storage engineering group, we have the distributed storage team. We have a focus on software-defined storage. Our two major offerings are our block storage via OpenStack. Internally, we call this Bloomberg Cloud Compute, or BCC for short. This is managed in collaboration with the compute engineering team. We also have our object storage. So this is the S3 compatible API. It's internally referred to as Bloomberg Cloud Storage, or BCS for short. Given the context we're representing, it shouldn't be a surprise. This is all backed by Ceph. So the focus of this talk is the QoS platform that we have on our S3 gateway. So the clusters that I'm talking about are heavily Rados gateway focused. In terms of traffic, we do over 1 billion S3 requests every single day. To give an idea of scale of the clusters, we have 4 separate Ceph clusters across 4 of our data centers. About 1,600 tenancies or so, or a tenancy is a Rados gateway user in this case. Approximately 65 petabytes of raw storage. And within each data center, we run about 4,500 OSDs and approximately 50,000 buckets total. So here we have a visualization of the cluster. The entry point for all of our users is a gateway host. This is the only visibility that the clients have into the system. So basically, they're not aware of the fact that we're running Ceph. They just see it as, here's a node they connect to and they do S3 stuff with it. It is worth specifically stating that a gateway here is not just the Rados gateway, it's also where our QoS and load balancer stack runs. So you can see that this is just the primary interface for the core of the Ceph cluster, where the mons, the managers, OSDs, and all that jazz live. Another interesting part here is, as we've mentioned earlier, we have a multi-site setup, so we run in an active-passive setup. Users interact with the active cluster, and the traffic gets replicated to the secondary. Where this is relevant for what I'm talking about is specifically that the QoS platform that we have is not just for client traffic. It's also used for the replication traffic as well, so we can gate that and ensure that that doesn't take down the system, essentially. So, how do our users expect to be able to use the system? In short, we run this as an internal cloud, right? So we are not the primary consumers. It's consumed by other members within the organization. The basic mantra that we have is that we want everyone to treat it like Amazon S3, good and bad. So some clients make very interesting language choices. As a result, they should be able to pick whatever client SDKs they want to use. We don't want to tell them, hey, that's a bad language, go use another one. We don't want to slow them down. Similarly, the available bandwidth and latency, it's fine until it's not. We provide a set limit on the things that they can do. If they have more that they want to be able to do with the system, then they can come and talk to us. They can make a compelling argument, and we can, try to help them out, essentially. And thirdly, it has to always be available, right? So similar to Amazon S3, you don't you should assume that S3 will go offline, but I would wager that most people don't. And that follows through in this system as well. It has to always be available. If we go offline, that has massive implications for all of our users. Similarly, in terms of user experience, everyone uses Amazon S3 very differently. So the usage patterns that we have for all of our users are drastically different as well. So we can't optimize for specific cases. The size of objects, even the traffic flow. So is it read heavy? Is it write heavy? The consistency of traffic loads over time. Do they do all their traffic at 8 a.m. in the morning? Do they do it constantly throughout the day? Like that sort of stuff. Even the lifetime of the data. We have some data that literally exists in the system for actual seconds, and then we have stuff that lives for years, whether or not the user intends it to. So with all of these things in mind, we can come up with a list of goals that we have for our cluster to try and keep everyone happy. And primarily, we want a consistent, guaranteed experience for our users with regard to functionality, latency, and throughput. Not just within the context of a user, we also want to manage the performance of the overall cluster. This is important for various reasons I'll talk about shortly. And thirdly, we want visibility into what the cluster is doing, right? If we don't know what the cluster is doing, it would be silly to assert that we are providing a consistent experience for our users. So this is where QoS comes in. It's not a secret, every cluster has a finite capacity, IOPS, bandwidth, compute, all that sort of stuff. QoS is a great way of trying to ensure the overall performance of your cluster and thus the stability, right? Like you have an overall limit on what your cluster can do, and you know that if you hit that limit, you're in a bad place. So you want to try and protect yourself a little bit. And the primary means by which you achieve this is two ways. One is verb level rate limiting. So this is saying you get 1,000 GET requests a second for a given user, for example. And then you have aggregate bandwidth throttling. So this is where, regardless of the number of transfers that a user is doing, you want to limit their bandwidth to a set amount. So they're doing, say their limit is 100 megabit, they're doing 10 uploads, doesn't matter. The total sum is 100 megabit, even for 1,000, it doesn't matter. It shouldn't exceed that limit, aggregate. So with this, we can come up with a list of the things that we want to achieve, or if we implement these things, then this will be a successful QoS system. Number one, it has to operate in layer 7 of the OSI model. So this is basically HTTP level or application layer level, right? So this is important because the level of information that we get out at this level in the stack lets you make high-level decisions based on, things like buckets and access keys and all that sort of stuff. Which, as you can see here, this enables QoS at both the access key and the bucket level. The access key or the user level is fairly obvious as to why we would want that. The bucket level is a little more interesting. This is for the case where users have public buckets that, for whatever reason, they write data into a public bucket and other people just read that data out via curl or something like that. So they don't have access keys, meaning this is a potentially exploitable part of your system where users can basically get whatever bandwidth out of it they want if you don't watch for it. Similarly, as I mentioned before, we want to perform QoS at the cluster level because we know what the overall limit of our clusters are with regard to network throughput and things like that, and we know that our network engineering teams would be extremely unhappy with us if we actually sustain those levels. We don't want to melt the NICs. Similarly, node level, we know what the limit of an individual node is. We know if we hit that, then we risk the stability of individual machines, which can have a rippling effect on the rest of the cluster. So we don't want to hit that either. And of course, the ways in which we want to achieve this are with verb level rate limiting or traffic policing and bandwidth throttling. And finally, it has to be simple to administrate. We don't want to spend a lot of time if our users make compelling arguments constantly for why they deserve more limits or something like that. We don't want to keep redeploying software. It should be as push button as possible. So some of the challenges that we face in this system are just real-time monitoring of the clusters, just having awareness of what users are doing and how much throughput does an individual access key get on a system. Like, you need to know these things before you can start making determinations on the kind of limits you want to put on them, right? You can't just suddenly install this and then everyone has 10 times less traffic than they did. And that sort of flows into my second point here. You need to understand how the system is behaving. So if your latencies increase by 10 times, say, over a given period of the day, does this actually matter? It looks terrifying on a graph, but does it impact your users at all? Some users, yes. Some users, no. But you need to know this, and you need to know what the potential business impacts are of these things. Another problem that we've had a lot of trouble with is distributed systems talking to other distributed systems. So I'll talk a little bit more on that later. And finally, we couldn't find any out-of-the-box solutions for this. So we looked around a bunch. If it exists, it's under a very interesting name because we couldn't find it, which was curious because this seemed like something that everyone would want. So some of the solutions that we looked at, we had a look at hardware-based QoS, the Rados Gateway level QoS that Ceph provides, and finally, software-defined QoS. We actually run hardware-based QoS in some of our legacy clusters right now. The installation process for this is reasonably simple of like where it slots into a graph. You can see here, it just goes between your users and your gateways, and then all of your load balancing in QoS gets performed by configuring the networking appropriately. But there are some problems with this. One, it's expensive. You're buying appliances from a vendor. There are support contracts. You have to refresh them every now and then. It's expensive. This also means that it's hard to scale. You're not buying a lot of these devices. They're really expensive on their own, and you know that the cost of buying them is basically multiplicative. You know you don't want to buy a lot of them. You shouldn't need to. And in terms of functionality, they don't aggregate usage across client IPs, so you can think of this as it sees each client IP address as an independent client. This sort of goes back to what I was talking about before with the distributed systems talking to other distributed systems. If every client IP is seen as an individual client, then this means that the way to get more throughput in a system from a client's perspective is get more client IPs. When you're running in a virtualized environment, users with relative ease can spin up as many virtual machines as they want. So if one user has, say, 500 VMs and another user has 50 and they all have dedicated IPs, then the user with 500 machines gets 10 times more throughput than the other. So it's incredibly exploitable. So moving forwards, we took a look at the Rados Gateway level rate limiting that Ceph provides. One, it lets you set rate limits based on tenancies and buckets. So it fulfills that requirement that it's no longer exploitable by client IP address. But as you can see, there were some issues that we had with this. Number one, the limits are per minute. So from a client's point of view, this leads to incredibly choppy performance where basically if they fulfill the requirement or they exhaust their bandwidth within a given, let's say 20 seconds, then for the remaining 40 seconds, they're not going to be able to get any requests through. It's incredibly choppy. The metrics as well. So the metrics for actually tracking this are tracked on a gateway level, and this means that if for whatever reason your user is hitting on one specific gateway, then depending on configuration, they're either going to get significantly... I'll step back. To work out the overall bandwidth that you can do when your metrics are tracked per gateway is you either need to do that annoying math where you work out the overall limit that you want and then you divide it by the number of gateways that you have, or you set the limits per gateway and just sort of deal with it. And the downside with doing this is that you either get way more throughput than you actually want in your system, or when users accidentally pin to a specific gateway, they're going to get way less bandwidth than what everyone agreed they would get. So this doesn't really work for most users. It also only supports traffic policing, i.e. limiting, say, to 1,000 GET requests a second. It doesn't do throttling. So actual transfers of large objects are going to go as fast as the network will allow, which is not something that we want to happen. Depending on the version of Ceph you're running as well, it might not even be available to you. It's only available after and including Quincy. And finally, Ceph still has to actually process this traffic, right? So if you have a user that is sending through 5,000 requests a second and they get rate limited, and that user doesn't care, they're not using the appropriate client, they're just doing it with curl or something like that, then they're just going to keep pushing until they get it. And this means that Ceph still has to receive 5,000 GET requests a second, it still has to parse them, it still has to go, oh, I'm going to reject that. And it has to, these are CPU cycles that it will spend doing it, right? It could be spending it doing literally anything else. So it's a waste of resources. So this is where software-defined QoS comes in. Being that it's software-defined, it gives you the flexibility to implement it based on whatever you have available to you at the time. So if you're in the HTTP layer, for example, you have things like, in this case, we use access keys. You can use the buckets themselves. You could do other things like, we know that this client belongs to these clusters get this much throughput. Like, you can do whatever your mind can imagine, essentially, because software can do that. It's more economical. There's no vendor lock-in, right? So being that it's generic software, if you're running on Linux, as long as the hardware that you're running also supports Linux, then you're good to go. You can buy off-the-shelf stuff, which is very nice. Scalability is also simpler too, right? So with the hardware-based solution, for example, you scale up by buying more things. With software in a well-distributed system, you just run more instances of that thing, be it on the hardware that you have, or when if you need to get more hardware, you can, but scalability is simpler. But that is basically all of that. So at this point, I'm going to pass over to Alex, and he will talk through the details of the implementation.
Good afternoon, CephLCon 2023. Who's excited? So I'm here to tell the lovely crowd here about the implementation of our software-defined QoS. So as always, let's start at the beginning. So the first step in our recipe is to parse the network traffic coming in. When a request comes in, we need to get all the information we need out of it. We do this at the L7 layer with verbs, as well as like access key in the query parameter, as well as we also need to look at the lower level and get the packet information, which is mainly we're looking for size, if it's upload or download. Once we collect that information, next step, we need to aggregate these metrics across the cluster. The goal of the software-defined QoS is to track you across the cluster and be able to manage your usage across the cluster, not just on a node level. Next step, we need to calculate violations. So we set a bunch of policies about what a user can and can't do, how much bandwidth they have, how many verbs a second they have, and we need to calculate if the limits we've set and these policies we've set have any violations for that second. Once this is calculated, we need to enforce these limits. So as you'll see in our architecture, we have a service that knows about these violations, but these violations need to be enforced and prevent any further traffic from coming in that second. We do this two ways, right? HTTP verb limiting, and on the lower level side, bandwidth throttling. And as always, rely on a backup plan. You never know when the system's going to go down, when you need to change anything. You always got to be safe than sorry. So we got the recipe. Let's take a look at our ingredients. So our software stack, we have two very well-known technologies and two custom technologies that we've built. So HA proxy, very, very well-known. Reverse proxy, I think it's a very popular choice amongst the crowd. I hear a lot of people using it. So it doesn't really need any further introduction. And of course, we have Redis, also another very popular technology. It's a very popular key-value database. We use this to store usage that a user has across the cluster. And then we wrote two. We have syslog server. Given from the name, it's pretty evident what it's doing. It takes logs, parses them, and sends them forward, relatively straightforward. And then we have the policy generator. This is sort of the brains of the whole QoS system. This is the one that checks the violations and makes sure those violations get sent back to HA proxy so we could stop them. Okay. So let's dive in a little bit more to the implementation detail. So step one was parsing our network traffic. As we mentioned before, our tool of choice, HA Proxy. One, it's very extensible with the Lua extensions, and we use the Lua extensions a lot to make sure the system works. So we co-locate this with the RGW node, and like I said, it has level 4 and level 7 support. So in a certain sense, it's listening on 2 ears for each request, right? On the level 4 side, we have the packet level information. This is a custom-written HA Proxy module that we wrote, and that hooks into HA Proxy and essentially retrieves the data. And then on the HTTP level side, we look for simple verb information and whatnot, an access key, and that's how we're also able to determine that user. And then we pass that over to the syslog server. So second step, we aggregate these metrics across the cluster, right? We need to follow this user. So the syslog server maintains 2 queues, one for L4 information and one for L7 information. It batches these across if there's a fill up in the queue, and then flushes it out to Redis. So here we have a example. We increment a verb for a given epoch, which is just a certain second, a user with an access key, and then we aggregated 3 puts for that epoch. And then we forward over that information to our Redis server. And then here's Redis. It maintains all the information, like we mentioned. We have, like we said, HTTP verb information for a given verb prefix, as well as data transfer information. And then we track this per user for upload and download. And luckily, we set a very short time to live of 2 seconds. So we have a very consistent memory usage for Redis. So it's actually, Redis is not really a bottleneck in this architecture at all. So that's the big plus. Okay, so we've aggregated these statistics, right? Next thing we need to do, calculate these violations. So this is the second customer piece we wrote, the policy generator. It actually doesn't generate the policies, more like generates the violations. But as we can see here, we co-located with the Redis server. And what it does, we have a big process here. First thing you do is scan Redis. We scan Redis in chunks. So once we get a batch of Redis data, and like we said before, that was like verb, epoch, user information, it takes that batch of data and forwards it over to another processing thread, and then reads another chunk, forwards it over to another processing thread. These processing threads read our policies that we've determined beforehand, and then it checks against violations. Once we find a violation, we need to fan it out. And this has to be quick and responsive. So what we do, we have a separate thread for each HA proxy, and then that maintains a connection to each HA proxy. And then we fan that out. So the violation is sent to all the HA proxy nodes, which are, like I said, co-located with the RGW. So that's how we get the information that we have a bad actor of sorts, or at least someone that's violated one of our policies. And then once we've calculated that, we need to enforce it. So here we go. The policy generator, like we said, sends all the violations over to HA proxy. HA proxy, we have a Lua extension that's listening to a port that we know HA proxy, that policy generator is going to talk to us about. So it's listening on that port, and then it takes all these policies that were violated, and then it stores them. One, we have 2 things, right? The HTTP level policies, those are stored in a Lua dictionary, and that's maintained in Lua itself. And then we pass over any violations for bandwidth down to the HA proxy C code level, and we store that in a K hash map. So now we have the data, we have the violations in HA proxy, and now we're ready to go to start enforcing them. So let's say we have a new request coming in from one of our applications or users. That request comes in, and like we said, HA proxy listening on both ears. So on the HTTP level side, it checks the verb violation. This is against the Lua dictionary that we maintain. So we find that a user for that given epoch used too many gets per second. If we have a limit at 10, the 11th one will hit this, and then we'll return a 503. Next step, on the L4 side, we check for bandwidth violations. This is done when we read in the C code for HA proxy. When we read a packet over it, we check it against this K hash map that we've created, and that has the violation. So if we see that, we need to throttle that user for that given second until they're ready to go again. We do this through just sleeping them for a couple of milliseconds, and then if the epoch is updated, we're ready to receive more connections. So this way the user is not, user's workflow is not jarred, it's just merely throttled. So that's how we enforce it. Here's a high level one. So this is our architecture that I just described. We have Bloomberg applications coming in, they hit the HA proxy on the gateway. That's the first thing they always see. We parse that traffic information from there. We take that, and then we need to aggregate it, step 2. That goes to the syslog server, as we said, that maintains the data, batches it if it has time, and then sends that over to Redis. Redis, now, we're still maintaining all the aggregated data that a user has across that cluster, and then that has like a short time to live, so like we said, there's no memory issue there. And then we have policy generator, which is reading from Redis in batches, checking against the current epoch, determining if there is a violation, and then once we calculate these violations here in policy generator, we then fan them out to every gateway. And that's back into HA proxy. HA proxy has the given information it needs to then throttle or deny users. And then if everything's good, you just go down to the RGW, no problem. So it's a very targeted and dynamic QoS system. Like we said, it's on the tenancy level. We do this, a user has a certain amount of verbs it can access, they can use it for a second, as well as a certain amount of upload and download bandwidth that we're allowing them. This is on tenancy level, so we track by access key. Next thing, obviously, the metrics are cluster-wide, which is one of the prerequisites we came up with for implementing the system. Once we have the metric cluster-wide, right, we have these rate limits, and the good thing about it is the rate limits are configurable, as well as the bandwidth limits. So we could give a certain access key, a certain power user, more bandwidth, more verbs, depending on their workload. They could have more gets if it's more read-only, or less gets if it's not. So it's very dynamic. We could update this at runtime, the policy generator scripts, reload every every so often. And once they reload, we have all the new policies that we need to keep enforcing. And then it's obviously custom because it's per user at that point. They don't just get the default. And then hopefully this is the only QoS taking effect. This is our most powerful QoS to track a user across the system. But as we know, in a distributed system like this, things break. If our active QoS system goes down, we don't want to be caught naked, essentially. So next step, the final step, right? Always rely on a backup plan. So this is node level information and QoS. So we don't want a single node to be saturated to the point where it can't process any more requests, as well as we don't need connection to all the other nodes, like the Redis server or whatnot, in order to QoS a user and protect the RGW from resource depletion. Node level, the metric aggregation is anonymous across that node. So it's not per access key per node, it's just per node. So a single given node can, let's say, only handle 1,000 gets a second. Doesn't matter who uses that, which user uses that. Once we see that, it'll be that whole traffic going to that server will be stopped for that second. These are meant to be set really, really high. And this is a last case scenario. We base these based off the network, the hardware resources we have on that single node. We know what it could handle, as well as historical traffic distribution. So given these two things, we sort of have some set limits to protect the node in case anything happens or a certain node just gets all the traffic, unfortunately. This is a very simple implementation. If anyone uses HA proxy at least a little bit, you would have heard of the stick table. So we use a simple stick table that has all the information we need. HTTP verbs per second, HTTP request verbs per second, upload and download per second. And then we enforce this through the configuration. So here's our QoS system in action. Might be hard to see, but we gave each user, we have two users here, a certain amount of get requests, a certain amount of head requests. So 450 gets, 300 heads, 150 puts, and then 100 deletes. As we can see here, maintained pretty stably across the cluster throughout the workload we tested. And each user gets a fairly consistent one. Like we mentioned, this is a system, we're not charging per request. It's mainly to protect our system and prevent our system from getting overloaded. We accept a small margin of error if it means the safety of our systems. So there was obviously challenges, not a fairly easy system to implement and run at scale. So bandwidth throttling is something we really had to roll up our sleeves and get into. We had to look at the HA proxy code and really extend that. And then, of course, we have clients with different bandwidth patterns, uploads, downloads. It's hard to really maintain that and make sure every user is happy. So that was a pain point that we had to overcome. As well as real-time processing. The system has to be quick. There's one brain, and that's the policy generator. This policy generator has to fan out the violations in rapid time. If it's a second late, there is no QoS because it won't enforce from the previous epoch. So high performance at the policy generator level is key And that's something we can't have stale policies en masse. Of course not. So future plans, we want to keep extending the system, keep having more and more dimensions that we could have permutations on, IP level, bucket level, like we mentioned, and different mixes of that. Pretty much anything you could think of. The system is fairly extensible. You could just add, a different hook and calculate that data, and the policy generator knows what to do. We also want to have it even more dynamic. Right now, it's a user gets a certain quota, but not every user is using that quota all the time. If we have a certain amount of bandwidth that we know we could service, there's no reason to slow down a user or deny a user when we have more bandwidth to take up. So in the sense, we want it to be dynamic across the network capacity we could have, and give a user more than they're even allowed to if we have quiet users on the rest of the connections. As well as priority management system. So we have some important users that are a little bit more critical to our business and our infrastructure. If we have some sort of bottleneck, we should give them priority. And yeah, that'd be a nice feature for sure. We also want to support connection limiting. There's always going to be some overhead with connections. We want to keep that to a certain limit and be able to enforce that. So I think that's also something we're working on right now. And also, as you might have seen in the implementation detail, it's not a lot of Ceph terminology or jargon. It's fairly agnostic. It's a QoS system that could be very easily extended to protect any system. So we want to make it a little bit more generic, something that we could use to protect any service and have it more, widely adopted. Of course, we want to contribute this to the open source community. Everything we do, we have an eye on open source. So, of course, the HA proxy patch is coming, as well as the whole QoS system. This is something that everyone will be able to get and see shortly and play around with, and please give us feedback on how we can improve the system. Okay, thank you. As always, I'd like to remind you, I'm sure you've seen our booth. We're hiring, of course. Please talk to us if you have any interest. Any of the Bloomberg people, we're all happy to talk to you. We've talked to a lot of you, too. It was a great time talking with everyone. So I'd like to open the floor up to questions. Anyone has any?
Very nice talk. So about the rate limiting itself, do you also attach costs to requests? For example, a GET request, but if it's a listing request of a bucket, that is far more expensive than a plain GET of a small 4K object, for example. Yeah. Does the system do something like that also?
That's a good question. Yeah, it's a good question. We don't have that functionality right now because not every GET request is built differently. As well as it's sort of like if you have a list, right, that's kind of on the L4 level, like the bandwidth does sort of affect that to a certain extent. We'd like to be a little bit more intelligent with that, but it's hard. Like you still sort of get that on the bandwidth level, but yeah, good question. Anything else? No? Of course, yeah.
So when you talk about nodes here, you're referring to RGW nodes as the node metric, right? I mean,
it's a server. Yeah.
Okay, the HTTP server. Okay.
Yeah, just a given server. Like a node, it has all these little services running on it. Yeah. Okay. Anyone else have anything?
It is worth clarifying that we are talking about an individual host. We do run multiple Redis gateways on a given host. So this is purely about protecting that host from being overrun and dying, not so much an individual gateway. I don't want to say you can run as many gateways as you want on a host, but it's about protecting a host, not necessarily a Redis gateway.
Okay. Anyone? All right. Thank you. Thank you for being a lovely crowd.